Thank you, Professor Guild, for the introducing. Hello, everyone. I'm Yihui. I'm a PhD student from Distributed Electrical Systems Laboratory at EPFL. On behalf of my co-authors, Paolone and Fabrizio Sossan, I will present the paper titled Effect of Voltage Source Converters with Electrochemical Storage Systems on Dynamics of Reduced Inertia Back Power Grids. As widely recognized, the power grids are transiting from synchronous generator-dominated grids to the grids with massive connection of power electronic interface renewable resources. That means they're moving towards large-scale low-inertia power systems. This will lead to fast electromechanical dynamics when subsequent to contingencies and bring challenges to system stability and frequency control. One example is this famous blackout happened in South Australia in September of 2016. To handle these challenges, one of the proposed solution is a battery storage system. In this context, it is of our interest to study the interaction of high capacity converters with the low inertia back power grid systems, and also to quantitatively evaluate the impact of converter control loss. However, we found few studies that conducted this analysis relying on electromechanical transient model. Why it is important to conduct this analysis using an electromechanical transient model? Because as also detailedly reasoned in the reference below, the phasor-based studies may exhibit limitations when dealing with broadband signals, especially for the power system with increasing share of converter-based renewable resources. Therefore, this paper relies on the computational approach that is based on detailed electromagnetic transient models. By means of full replica dynamic models of grids, converters, and controls, we assessed the impact of converter interface to battery storage system on the dynamics of reduced inertia power systems. And we also evaluated the performance of the two main control strategies for the power converter, namely the grid forming versus the grid following converter. So the reduced inertia back power grids that we use are extended from the IEEE 39 bus benchmark power grid, whose topology is shown in the right side figure. By replacing the 4 synchronous generators with 4 type 3 wind power plants, we reduced the system inertia to 1/4 of the original benchmark system. And then on the right side topology graph, we have the presence of converter interface, the BSS is considered. For the 39 bus benchmark power grid and its extending configurations, we have built full replica dynamic models. So in the following few slides, we are going to walk you through the detailed model of each component. First, for the conventional generation, which relies on both hydro and thermal power plants, the models of synchronous generators, governors, and excitation systems are exactly those have been proposed by the IEEE working group, where they have elaborated the 39 bus benchmark grid. So here it consists of a 6-order state space model for the synchronous machine. Prime mover, depending on the type of the power plant, we have hydro or steam turbine, and the corresponding governor. Then we also have an excitation system associated with an automatic voltage regulator. For the load, we adopt the EPRI load sim node model, as you can see from the active and direct power equations below, and it's a voltage and the frequency dependent load model. Regarding the wind power plant, we implemented the type 3 wind turbine model, which consists of a double phase induction generator with an averaged back-to-back converter. Here to note the reason why we have chosen the type 3 wind turbine. In general, there are 4 types of wind turbines. Type 1 and 2 are fixed speed wind turbine, which are suffering from the fact that when a gust of wind hits the turbine, a fast and strong variation of the electrical outpower can be observed. So there comes up with the type 3 and 4 wind turbines, which are varied speed wind turbines. For the type 4 wind turbines, because the power converters are actually put in series between the wind turbine and the power system, the power converter and its associated filter has to be rated at 1 per unit of the total system power, which makes it difficult for the filter design and also costly. In addition to this, the efficiency of the wind generator is largely depending on the converter efficiency because all the power has to go through the converter. So in contrast, the type 3 wind turbine, as you see, the configuration like this, it improves the efficiency, it avoids the disadvantage of the type 4 wind turbine and improves the efficiency while reduce the cost. Therefore, we say that type 3 becomes popular and we pick it in our study. As for the Gov Converter Interface, the BSS, we have considered 156 BSS connected on the same AC bus, and each of these BSS is composed by two cell stacks in series, as you see here. Each of these cell stack is identical to the battery system we have in our laboratory. So as we consider that the batteries, converters, and their controls are all identical, so therefore they have been replaced by this equivalent model where we have all the 156 stacks are connected in parallel on the same DC bus and interfacing with the AC grid through a single equivalent converter. As for the model of the single cell stack, we model it as a third order model with SLC dependent parameters. Those parameters are identified using measurements of lithium titanate oxide BSS from our laboratory, and then the target power is achieved, as I illustrated before, by composing the two cell stacks in series and then put the series stack in parallel. Okay, so for the converter, although the multiple parallel converters are represented by a single converter, this single converter itself is a fully modeled 3-level neutral point clamped converter by using 12 IGBT diode pairs and 6 clamped diodes. As you see here, this is the exact configuration we have in our model. As mentioned before, we will compare the two converter controls. First, the grid forming control. It allows the converter working as a voltage source by controlling the voltage magnitude and angle at the point of common coupling. Here we adopt a PLL-free grid forming control, which is proposed in the MyGrid project, which you can find in the reference below. This type of grid forming control directly links the active power exchange with the angle difference between the grid voltage and the modulated voltage. Such a control architecture not only allows the synchronization with the grid, but also intrinsically allows the converter to deliver in primary regulation. As for the grid following control, it allows the converter working as a current source. The injected currents are controlled with a specific phase displacement with respect to the grid voltage at the PCC. So here we let the grid following control operated with grid supporting mode by adding a high level frequency and voltage regulators with droop characteristics. So now, as we have in the full replica dynamic model of the 39 bus benchmark power system and its extending configurations, we use the OpenRT in Maxon real-time simulator to implement the 3 full replica dynamic models. Here, just to sum up the 3 configurations, we have the config 1 is the original 39 bus benchmark power system with 10 synchronous machines, and config 2 is the reduced inertia 39 bus power system with 4 wind farms, and the config 3 is achieved by connecting a converter interface, the BSS, to this reduced inertia 39 bus power grid. All of the 3 full replica dynamic models are open sourced and are available in the GitHub account of our laboratory. So to evaluate the post-contingency dynamics, we consider the 2 study cases. In case 1, we have tripping of generator 6, which causes 800 megawatt power tripped. And case 2 is the tripping of generator 4, causing 545 megawatt tripped power. Here in this table, it shows the pre-contingency node-out power injection for configure 1 and the configure 2. I didn't put configure 3 because since they are the same as configure 2, sorry, because the pre-contingency operating point for this connected BSS is 0. With this table, I would like to emphasize that the case 1 is used for 2 objectives. The objective 1 is to evaluate the impact of reduced inertia, because as you can see that the operating point of generator 6 are very close for the two configurations, the config 1 and config 2. So it can be used to compare the original 39 bus with the reduced inertia 39 bus grid. And then, then this contingency is also used for evaluating the effect of BSS on the system dynamics and for the comparison between the two control laws. As for the case 2, the tripping of generator 4 is considered as it because it generates among the largest frequency nadir. So first, let's take a look at the impact of inertia reduction. After the tripping of generator 6, with respect to the configure 1, which is the original 39 bus benchmark power system, the configuration 2, the reduced inertia 39 bus power system, exhibits much faster frequency decrease, as you can see from the frequency decrease velocity here, and it has much lower frequency nadir, as well as longer transient to reach a steady state. Now, in this slide, we quantified the impact of converter interface to BSS and the comparison between the two converter control approaches. From the frequency trajectory, we observed that with BSS, the frequency decrease velocity is slower and the frequency nadir has been increased around 1 Hertz. As well, for the transient interval, it has been reduced by a factor of 2. In terms of the post-contingency frequency dynamics, the two controls cannot be easily differentiated. However, if we look at the PCC voltage here, we observe that for the grid following, the PCC voltage dip reached 6% of the nominal voltage, whereas for the grid forming, the voltage decreased only around 3%. This is because the grid forming control allows the converter operating as a voltage source, which is capable of better sustaining the PCC voltage. In case 2, we have relatively less power being tripped, while still we see that with BSS, the frequency nadir has been increased evidently, and the transient interval is reduced from 75 seconds to 35 seconds. Again, from the dynamics of the voltage at the point of common coupling, we see that we demonstrate that the benefit of grid forming converter in maintaining the PCC voltage during the transient. As you can see from the figure here, for the grid following converter, the voltage decreased around 6%, whereas for the grid forming converter contained the voltage reduction within 3%. So to conclude, in this paper, we proposed the 3 39 bus power grid configurations as extension of the IEEE 39 bus benchmark power system. Correspondingly, we built 3 full replica dynamic models that are executed on the real-time simulator to reduce the same contingency and conduct post-contingency analysis with respect to the system dynamics. And the simulation results verified the substantial influence of the inertia reduction on the post-contingency dynamics of the system, and also quantitatively proved the connected BSS assessed in limiting the frequency nadir and in damping the frequency oscillation. We also evaluate the performance of the grid voltage at the PCC of the converter, and it demonstrated the benefit of grid forming converter in maintaining the PCC voltage during the transient. I would like to thank you for your attention, and I'm glad to take your questions.
Thank you for your interesting presentation. So I had a question about the inertial effect, because in fact, we don't see so much difference for the inertial effect between grid forming and grid following. So have you taken into account the filtering that you have to apply on the in case of grid following, because you have to filter the frequency? So your conclusion isn't very clear about that, because there is a clear difference between grid forming and grid following and grid following in terms of inertial supports. So I didn't see any clear point about that in the conclusion.
You mean like here in this case, when we compare the frequency dynamics of the two controllers?
Yes.
Yeah. So indeed, in this power system, we didn't see much difference. But in my opinion, in this system, or even though we call it reduced inertia, we still have 6 generators, synchronous generators. So in fact, although the inertia has been dramatically reduced from the original system, in this transient, what I think is the inertia effect of the synchronous generator still dominated. So here we cannot differentiate because the advantage of the grid forming in the inertia is not big enough to show it, to show the effect. And if what we can do is to increase the capacity of the converter, or we reduce the inertia more so that we can more clearly say the difference. Yeah. Yeah, here we have the really not able to say because in my opinion, is dominated by the inertia of the synchronous generator.
Yes, it's true that you have a large system, so just one system among many others. So
yeah,
I understand. But what would be your advice about the influence of the inertial effect on the storage element itself? Do you have an idea about that? Because if you bring inertial effects in the system, it means that the energy comes from the battery. And do you have an idea about that? Is it possible to provide this battery? And what about the solicitations of the battery? Do you have an idea? I know it was not really the core of your paper, but it's linked with your paper.
Yeah, I see your point. So what you mean is like what we can maybe how to identify the inertia this battery or this VSC system can provide in the system for this power system. So indeed, it is not so straightforward to identify this the effect of the VSC control, the converter control, and how much inertia it can provide, and also it depends. I think it depends on the capacity of the converter, and then it also depends on this controls we have for the converter. Well, then for how depends on how fast you can provide the inertia to the system. We have to maybe do analytical study to know how much we can provide.
Okay, so last question. I see last question from Keith Bell. Can you read this question?
Yeah, I think I can. I can read the question. What key performance issues would you have missed if you had used a simpler phasor-based modeling instead of the full EMT modeling that you've used? Could those issues be resolved at the equipment design and grid code compliance testing stages, or would they remain in the final operational context and need to be addressed by the system operator through changes to the system's operating state? So for the first question, so I would say I would give example of some problem we could have is the post-contingency protection strategy. If you, for example, we have characterized UFLS or under frequency load shedding strategy that based on using Rokoff criteria. In this context, if you have the phasor-based modeling, it will not catch the dynamics of the system after the contingency, which will totally not able to give a right UFS strategy after contingency. Even in this condition, because if we have the fully modeled system that we are able to capture dynamics, we can also use it to test the difference between the algorithms used to measure the frequency, and based on this we do the decisions on the UFS control. And for the second question, I'm not really sure I understand it. So what you mean is this issue could be resolved at the equipment design and the grid code compliance testing stage, or would they remain in the final operational context and need to be addressed by the system operator through changes to the system operating state? Yeah, what I'm thinking is like, it is difficult to address all the problems using the simulation strategy. There are a lot of problems will come up when you have the design equipment, and also depends on the code of the grid. So indeed, I think there are a lot of practical issues that has to be addressed by the operator, and when they are doing the operating on the practical operating stage. I hope it answered.
Thank you for your answer.